this video, we're going to look at projectile motion. So we're going to look at motion in two dimensions, essentially. In previous videos, we've looked at motion in one dimension, but with projectile motion, if you think of a javelin being thrown, it moves in an arc type of shape, so it moves forward in the horizontal, but it also moves up and then back down in the vertical, so it creates a curved path. A curved path can't be considered to just be in one dimension, like a straight line, so we have to think of it in two dimensions. So let's just take an example question. Now, we're not going to look too much at the Suvat equations in this video and consider how they can be used to solve problems of projectile motion. We're just going to look at a few basics, and then we'll get onto the Suvat equations in the next video. So the example is, a particle is fired into the air from the ground with an initial velocity of 2 meters per second at an angle of 60 degrees to the horizontal. Taking the particle's start position as the origin, find the horizontal and vertical components of the particle's velocity, and hence state the initial velocity as a column vector. So there's a lot there to unpack, but let's just think about it. So the particle is fired with an initial velocity of 2 meters per second at an angle of 60 degrees. So it's very important to note that this velocity is a vector. So it's always a vector, but when we're talking about one dimension, it's not too important. We don't have to be as aware of that, because even though it's a vector, we can sort of consider it to be a scalar. We just have to worry about the sign. Is it positive or negative? But now it's actually moving in two dimensions, so it's going to have horizontal and vertical components. So this is a vector we've been given because we're told its velocity is 2 meters per second, but also the angle that it's fired at to the horizontal is 60 degrees. So let's just draw a diagram to really express what we mean. So the following diagram, let's consider. U is what I'm going to use to represent the vector representing the initial velocity. So the initial velocity is U. I've put it in boldface because it's a vector, and it's this vector here. So the ground is this dotted line, and the vector is at 60 degrees to the ground, and where the vector is originating from on the ground, that point is the origin. And I know that the vector has length 2, because when we're told the initial velocity is 2 at a certain angle, that means that the magnitude of the velocity is 2, so the speed, if you like, which is magnitude of velocity, is 2. But then, because we're told an angle, we have sort of all the information on the vector that we need to find its components. If you're not too sure about how to work with vectors or how to do trigonometry, because we're going to have to do trigonometry here, you should watch the vector videos and the trigonometry videos in this set of videos. So I'm going to just assume that you're pretty confident with vectors and with trigonometry. So whenever you get a problem like this, this is sort of what it's telling you. So when it says the velocity is 2 meters per second but in a direction, it means, a specific direction defined as an angle to the horizontal. It means that the velocity is a vector with length 2 in this case, and then the angle you can use to show how the vector fits into your coordinate system. So I'm assuming that the origin is where the vector is originating from. So the ground is my x-axis, and then there would be a y-axis perpendicular to that going through the origin there. So in this coordinate system, I want to find the components of my vector, u. Because I know its length and I know this angle 60, I can actually do that straight away using trigonometry. Okay, so how do I do that? Well, I know that this vector here, let's call it h, plus this vector here, v, is equal to u, because that's how vector addition works. So if I add h to v, I would get u, because they're end to end. So if I can find the components of h, the components of v, maybe I can find the components of u, because if you look at it, well, h only has a horizontal component. It's only got a horizontal component, it's not got a vertical component because it's completely horizontal. And v only has a vertical component because it's completely vertical. So if I can find the vertical component of v and the horizontal component of h, then I've essentially found the two components of u, because I know that h plus v is u. So let's look at what I mean. And well, let's look at how we can do this. We can do this using trigonometry. because we know that the length of h is the side length of this triangle and the length of v is the side length of the other side of the triangle. And we have, for instance, that h is adjacent to 60 degrees, and then we have the hypotenuse is 2. So if we think of SOHCAHTOA, we can use that cos of 60 degrees because we've got adjacent and hypotenuse, so that's CAH. So cos of 60 degrees is the adjacent over the hypotenuse. So cos of 60 degrees is the length of this h vector, that's the adjacent, divided by the hypotenuse, which is 2. Rearrange, we get that h equals 2 cos 60, which is actually 1. So you can, maybe you just know this, that cos 60 is a half, or you can plug it into a calculator and you'll get cos 60 is a half. So 2 cos 60 is 1. So the length of h is 1. That's what we've just said. If you look here, the length of h is 1. But that actually means that h is just the vector 1, 0, because h is a horizontal vector, so it doesn't have a vertical component. So it just moves 1 in the x direction and nothing in the y direction. So if you think about the vector v, we do the same thing but with sine now, because v is opposite 60. So you've got SOHCAHTOA, so we're doing SOH. So sine of 60 is the length of v over 2, the hypotenuse. Rearrange, you get the length of v equals 2 sine 60, which is root 3. So again, I've used a calculator, or maybe you just know using exact triangles that sine 60 is root 3 over 2. So if we times it by 2, we get root 3. So v is just the vector 0, root 3, because it doesn't have a horizontal component, it's just a completely vertical vector. So it goes 0 in the x direction and root 3 up in the y direction. So, as I was saying earlier, we know that u, our initial velocity vector, is equal to h plus v, because h and v are end to end. So the way you would add vectors up is place them end to end, and then you draw a vector from the start of h to the end of v. In this case, that is u. So we know that u equals h plus v, but we know that h and v are these two vectors, 1, 0 and 0, root 3. So u is just 1 root 3. So in finding the components of h and v, we actually straight away found the horizontal and vertical components of u. They're 1 and root 3, so we know the exact vector now that u is. So this can often confuse people because it's a bit strange. So you say, well, what is u? It doesn't represent the path of the particle. The particle starts by moving in the direction u is pointing, but we don't know it just goes in a straight line like that. It starts to curve and takes a kind of arc shape, but u just represents its velocity. So the magnitude of u is just the magnitude of the velocity, so essentially the speed. So the longer u is, bigger u is, then the faster the initial speed of the particle. So the important thing to know is that in general you can always do the same thing. So what did we do? We found that the horizontal component is 2 cos 60. It's the magnitude of the vector times by the cosine of the angle the vector is making with the horizontal. And the vertical component is the magnitude of the vector times by the sine of the angle it's making with the horizontal. And this will always be true. This is true when you have a vector representing velocity, or sometimes you might have other vectors representing force or something like that. You can always resolve, it's called, so you can resolve the vectors into their horizontal and vertical components as long as you have the magnitude and the angle the vector is making with the x-axis. So in this setup you can always do that. You just get the magnitude times cos of the angle and the magnitude times sine of the angle. So that's the important thing to take away. And then you can, if you want to, actually calculate what they are. In our case, we've got quite nice numbers, but often people wouldn't bother because the numbers wouldn't be very nice. They'd just be like horrible decimals. So you could just leave them in terms of cosine and sine.
And his happiness was one with hers.